Hey guys, welcome back to my YouTube channel. So today we are going to continue our discussion on the combination circuit. So we have completed the full adder and the half adder. So let's today see how the half adder circuit will work, half subtractor circuit will work. So these are all just normal mathematical functions, so you guys can enjoy it. So let me complete the truth table for half adder. So A, B, here the thing is not sum, which is different, or not carry, which is borrow. Okay, so this is borrow. BB may confuse, I am mentioning it B not. So 0 0 0 1 1 0 1 1. So this is normal. So 0 subtraction 0, the difference will also be 0, and also no borrow needed, so that is also 0. So here 0 cannot be subtracted from 1, so we need to get borrow 1 and the difference is 1. So here this can be difference is 1, no borrow needed. So here if we subtract it, difference will be 0 and borrow is also not needed. Okay, so if we write, so the D, the difference which is equal to, here also the same thing like XOR gate that we are getting, so which is also equal to A XOR B. Okay, so here B naught, so it will be equal to A bar B, because it is only 1, so this can be directly represented as A bar B. So this is half subtractor, so this is fine. So let us go to full subtractor. So that will be quite confusing, so please watch carefully. So this is full subtractor. Okay, so let me draw the truth table. So you guys can also try it, so please pause the video and try to answer it. So if you guys able to achieve it, please post in the comment section that you guys able to hit it. So that will be nice if you guys get it. So A, B, C, D and B bar. So 0 0 0 0 0 1 0 1 0, so 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Okay, so here the thing is same, so no borrows here, no difference is here. Here if you see, here there is nothing needed, but here we need one borrow and the difference is 1. So here itself we need one borrow, and here the difference will be, here itself will be, that is changed to 1. So here you see that is 1, so if we subtract this, this is needed. So here we need one borrow, and here if we subtract it, then that will be 0, so that is 0 1. So here there is no borrow needed, the difference is 1. So here this will be fine, no borrow needed, and the difference will be 1, and 1 minus 1, that will also be 0, and no borrow needed, so 0 0. So here this will be, difference will be becoming 0, borrow also not needed. Here itself the difference will become 0, so here we need to get one borrow to complete the subtraction, and the difference will be 1. Okay, so I hope you guys able to get it right. So this is normal, so let me explain the last one. So 1 1 1 is there, right? So if we subtract this one, here itself will be changed to 0 1. So in order to complete this subtraction, we need a borrow, and this will be changed to 0. So that is what we have made it. So one borrow, and the difference is 1. I made a mistake here, so difference is 1, because that is a different borrow is needed, but that will not be considered. So number of, here if you see, the odd number of ones will be taken into output outside. So that is what the case here. So borrow is needed, but the difference, that one we will not consider there. So that is what the case. So if we take this one, let me take 1 0 1. So here if you see, the difference will be 1, and 1 1, that will be changed to 0. So no borrow needed, and no difference is also there. So that is one thing. This is how we completed this truth table. So let us draw the difference. So D, which is equal to summation of min terms, which is 1 comma 2 comma 4 comma 7. You have already seen this. This is similar to that one, XOR. So A XOR B XOR C. So for full adder and full subtractor, both we are getting the same. So let's see for borrow whether it's changing or not. So borrow, if we write in a min term, that will be equal to 1 comma 2 comma 3 comma 7. So if we use the K-map and write it, then this will be A bar B plus A bar C plus BC. So only A has a bar about it. So even, or this can also be written as A XOR B, or not like that, A bar B, A XOR B dot C the whole bar plus A bar B. So this is another notation that you can follow. So this one we have derived with the use of K-map only. So if you guys have a time, please make a note of it, or you can even try with the K-map how to implement it. Okay, so from here we are completing all our discussion on full adder and all the things. So let's see what is mean by ripple adder. Ripple or parallel carry adder. So ripple or parallel carry adder, both are same. So ripple or parallel carry adder. Okay. So let us draw the black box here, the same full adder. Okay, so let me take it. Okay, everything is full adder. And everything has full adder requires 3 input. So one is we know that is A naught, B naught, and this is C in, means previous carry. So that will be considered C naught most of the case. So here we will get S naught, and this C1 which will be fed as input to this one. So this is everything we know. So this is C1. So here we will give 2 input, that is A1 and B1. Then this carry which will be represented to this one. Okay, so this is C2. Then this carry will be going to this one. Okay, so this is C3. So which is A3, B3. Here we go A2, B2. Okay, so here it will come as S1. So here it is S2. Here it is S3. And here it is C4. Okay. So I hope you guys are able to understand this, right? So this is how, why we call as a ripple or carry adder is that this one, the second one, it need to wait until the first one execution is getting over. So that's why we are calling as a ripple or parallel adder. So it will wait for until the output coming from here and then only it will start. So that is what the thing. So the total number of things that is required here is the, we usually require 4 number of bit for full adder if in order to mention or get into 4 bit. So here the total delay. So how much delay will come is there? This is one of the important term. So total delay which will be equal to n into the transmission, the propagation delay of each full adder. So this is full adder delay. So this is in full adder delay into n. So how many bits that we are using? So that much full adder delay that it will take. So the total delay TD can also be written as n minus 1 TC. So this is the TC is the propagation delay of the carry. So each propagation delay is carry plus max of TS or TC. So the TS is the propagation delay, some delay for each thing. So sometime in the last case, if the delay for S3 calculation is greater than S4 means, then we will take that into account. So that is what here I mentioned. Sorry to mention this. So this is TC. So okay. So TC. So TC is the carry delay of each F adder, each, not a single one, this is each one. So this is some delay. So okay, so this is one important thing, please make a note of this formula. So this can also be asked in any of these things. So we can implement even 8-bit parallel adder by cascading two 4-bit parallel adders. So since the propagation delay is like ripple adder from one adder to another, so we can even call that as a ripple carry adder. We can overcome this disadvantage of delay by using a carry look ahead adder, so that we will discuss in the next class. So please make a note of it. So I am giving you a question, please make a note of it. So the question is that, so we are using 16-bit ripple carry adder. So 16-bit ripple adder. So ripple carry adder. Everything has a delay. So the TC, the carry delay is 12 nanosecond and the sum delay which is equal to 50 nanosecond. So what will be the total TD? So please pause the video and try to answer it. So let me answer the question here. So now only we see the formula, that the formula is n minus 1 into TC. So n minus 1, so 16 minus 1 into TC, which is 12 nanosecond, plus max of 12 comma 15. So we could clearly see 15 into 12 plus 15. So this is max. So that will be equal to 180 plus 15. So answer will be 195 nanoseconds. Okay. So this is the question. So we can straightforwardly answer this with the help of the formula that we have learned. So this is the thing that I thought to say. So the adder and subtractor both has separate things, separate circuits, right? So is there any possibilities to combine both the things? So there is one thing called universal adder. Universal adder and subtractor. So it can do both adding and subtraction at the same time. So here I am going to explain that concept. So first let me draw the black box. So here I am going to take 4-bit only. So let's take 4-bit thing. So or else let's take a 2-bit. So now to simplify the thing, so let's take 2-bit. So this is full adder. Okay. So here the input A0 will be fetched directly. So here there is no difference in that. A0 will be given directly. Here A1 will also be given directly. Okay. So here there is an check that we are giving a control signal C. So this control signal only detect what kind of addition or addition or subtraction that what to be done in the question. So here this is an output. So this is a carry. So here this will propagate from here to there. Okay, so this is carry output. Okay, so this is one. This is some out. So let me draw it. So this is a control signal. So this is CTRL. So this is a control signal C. So here if you see, this one will be directly mapped to this one. So this one will be directly mapped to input. Okay. So here the B, the concept why we are using this is the addition can be directly done. So there is no problem in that. So A plus B is no problem. That will the full adder will do. So because this is a full adder, so this will do. But subtraction, when we go for A minus B, this need to be written as A plus 2's complement. So A plus 2's complement. Okay. So that's why we need to toggle the bit. So for now to do the 2's complement, so we are going to inverse it. So for that we are using the control signal bit. So whenever B is XORed with 0, we will get B. Whenever B is XORed with 1, we will get as B bar. So this control signal can be 0 or 1 based upon our thing. So if we need to add the input, then we have to use the control bit as 0. So this is for addition. So if we need to subtract the thing, we need to give the control signal as 1. So that is what thing. So now what you have to do is that we need to XOR the input every B input with the control signal. So let me draw a table, so draw a logic for that one. So this is the XORed output. So this is B0 and this is taken from the control input. So this is B0. Okay. So this is actually not bijected. So this is jump. So this C will go directly. So this one is jump. Okay. So I hope this is understand. This is A1. So here also same thing. We need to XOR it. Okay. So this is B1. So this is jump. Need to be XORed. So thing is that. So this is S0. This is S1. And this is C2. This is C1. So here we can even call this one as a C0. So C0 can be the same control input. So the thing is that when control input is 0, when control input is equal to 0, then there is addition. So this is an universal adder. So that will just do the normal addition. So A1, B1 which will be added to like a normal thing. How to mention is that A1, A0 which will be added with B1, B0 as we said. So when the control input is 1, so when the control input which is equal to 1, this is subtraction. So how we will be doing is that we will be doing A1, A0. The thing is reversed. So B1 bar and B0 bar. So this bar is considered as 2's complement. So because it is a complement of binary, right? So this is considered as 2's complement. 2's complement of B. So even we can done like this. So if for 2's complement we need to add 1, right? So for that we will be adding 1 also. So for that one we will be doing that case. So this is how we will be representing the case. So if it is done, we need to add 1 because we are using 2's complement, right? So this output, all the output will be added with 1. So that will be taken care after this one, this level outside it will be taken care. So for now, here if the control input is 0, so if the control input is 1, if the control input is 1, so we will be toggling each one. So which will be B0 bar and which will be B1 bar. So after we getting all the results, we will be adding 1 to that because we are using 2's complement method. So this is just a 1's complement. The just an inverse is 1's complement. So we will be adding 1 so that it is a 2's complement addition. So I hope this is understood, right? So this one addition will be taken care outside the circuit. So based upon this control input, the one will be added at the end of the logic. So after the transposing the output, like post processing the output, the one will be added. So I hope this one is understood for you guys. So if you guys have any doubt, please post in the comment section. I will there to solve your doubts. So like, share and subscribe the channel. Stay tuned for next lectures.